Hello, am I audible? Hello.
Yes, sir.
Okay. So today we'll discuss the characteristics of atomic spectrum. So the molecular spectroscopic methods, that means the molecular spectra are generally broad. These consist of number of closely spaced lines constituting what is called a band spectrum. The band nature of the spectrum is due to the number of factors like quantization of rotational, vibrational motions of the molecule, along with the quantization of electronic energy levels. So, in case of molecule, the molecular spectra is a band spectrum because the band spectrum of the molecules, due to different factors like quantization of different factors like so rotational energy levels, vibrational energy levels, along with the quantized electronic energy levels. And in addition to that, the width of the spectrum also dependent upon some instrumental factors, instrumental parameters like. But in case of atomic spectra, the spectra consist of a number of very sharp lines. So in case of atom, that means if the atomic samples are there, the spectra contains very sharp lines, and that is the characteristics of atomic species. It implies that this gives rise to line spectra. The atomic spectra generally more sharper because in the atomic system, the rotational and vibrational motions are not quantized. That means the rotational vibrational motion of the atom are not considered, and here only the transitions are observed among the different electronic energy levels of the observing species. So in case of atom, we are considering only quantized electronic energy levels because for atoms, the vibrational motion and the motion are not quantized. So here a typical atomic spectra is given in this figure number 7.2. So in this figure you can see the atomic spectra, so that will produce very sharp line. Now similar to molecular spectrum, the signals in an atomic spectrum are also characteristics in terms of three parameters. The first one is position of the line, and the second one is intensity, and the third one is width. So first we'll discuss position of the line. So in case of absorption, emission or scattering of the radiation, and if the species will be atomic species, the interaction cause transitions among the electronic energy levels only. And and here you have learned that in case of molecules, the interaction leads to transitions. Already you have already learned that in case of molecules, the interaction led to transition among rotational, vibrational and electronics energy levels, and also combination of these. But however, in case of molecular spectra, like in case of molecular spectra, here also the position of the spectral lines is determined by the difference in the energy of the different energy levels. For example, if E1 and E2 represent the energy levels of the higher and lower energy levels, if E1 and E2 represent the energy of the higher and lower energy levels, then the energy changes during the transition from E2 to E1, that is daily, equals to E2 minus E1, which is equal to h nu, that is equal to hc by lambda. From this, you can calculate lambda equals to hc divided by daily. Here h is the Planck's constant, c is the velocity of light, and nu is the frequency, and lambda is the wavelength of the emitted radiation. So the wavelength of the radiation is the characteristics of the atom of the particular element from which it is emitted. That means different atoms will emit light of different wavelength. Now the second factor is intensity of signal. The intensity of signal depends upon the population of the energy levels from which the transition is originating and the probability of such type of transition. And again, you have already learned, according to the Boltzmann statistical distribution, the population of the ground state, that is the number of atoms present in the ground state, is highest, and it keeps on decreasing as we go to the higher energy levels. That means the number of atoms present in the ground state will be highest, and if we'll go to the higher energy levels, the population or the number of atoms present in particular energy level will gradually decrease. So in case of atoms, the population of any excited state relative to that of the ground state is given by the Boltzmann distribution law, that is equals to, and that can be represented as n star by n0 equals to g star by g0 e to the power minus del E by kt, or you can write n star equals to n0 into g star by g0 into e to the power minus del E by kt, where n star and n0 represent the number of atoms in the excited state and ground state. Del E is the energy difference between the two different energy levels. G star and G0 are the statistical factors depends upon the degeneracy of the energy levels. K is the Boltzmann constant and having the value 1.28 into 10 to the power minus 23 joule per Kelvin, and T is the absolute temperature. Now let us discuss one example. The characteristics of yellow emission of the sodium vapor consist of a pair of lines at 589 nanometer and 589.6 nanometer. These arise from the emission of radiation by the gaseous sodium atom in the 3p excited state to 3s ground state. Compute the ratio of the sodium atoms in the excited state to the ground state. That means you have to calculate the ratio of n star divided by n0. And here you know that from the equation 7.1, you know n star by n0 equals to g star by g0 into e to the power minus del E by kt. Therefore, to evaluate the ratio of the atoms in the excited state to that of the ground state, we need to know the statistical factor G star and G0 and also del E. As the 3s and 3p energy levels have 2 and 6 quantum states, so that means the 3s energy level have 1 quantum state and the 3p energy level has 6 quantum states. The 3s energy level has 2 quantum states and the 3p energy level has 6 quantum states. So the statistical factor, that is G star by G0 equals to 6 by 2, that is equals to 3. And again we know that del E equals to hc by lambda, and putting the value of Planck's constant h, and putting the value of velocity of light, that is c, and here it is given lambda 589.3 nanometer, that is equals to 589.3 into 10 to the power minus 9 meter, and here it is considered the average of the two lines. So here the wavelength is considered as the average of the two given in the question. So in the question it is given that is pair of lines at 589 nanometer and 589.6 nanometer. So the average of the two will give rise to 589.3 nanometer. So that is 589.3 into 10 to the power minus 9 meter. And from this you can calculate the value of del E equals to 3.37 into 10 to the power minus 19 joule. Now putting all these values, you can calculate the ratio of the atoms present in the excited state to the ground state equals to 3.069 into 10 to the power minus 4. Now coming to the next factor, that is intensity concentration relationship. The intensity of the emitted radiation, that is P, is proportional to number of excited atoms, that is n star. That means P is directly proportional to n star, or P equals to some constant A into n star, where A is the proportionality constant. Now putting the value, so here P equals to A into n star, putting the value of n star, we can write P equals to A into n0 into g star by g0 into e to the power minus del E by kt. So finally, so that will become P equals to k into n0, because k, the value of k is, so it will take the value of k equals to A into g star by g0 into e to the power minus del E by kt. we can write P equals to K into N0, or P equals to K dash into C, because N0 is proportional to the concentration of the atoms present in the sample. That means the concentration of, that means the metal concentration. So that's why P equals to K dash into C. Now coming to the spectral line width. The lines are generally symmetric around lambda max, and the wavelength at which the intensity is emitted, the and the wavelength at which the intensity of emitted radiation is maximum. The observance is also maximum at the same wavelength. The line width is defined as the width of the signal measured at half of the height of the maximum signal. So that means this is the signal. This is the signal. So this is the height of the signal. Now the width will be discussed at half of the height, that is called FWHM, full wave half maximum, that is full width half maximum. So that means you have to consider the line width at half of the height of the lambda max peak. So this is the lambda max peak and its height is this much, and at the position of half of the height, the width of the signal is considered as the effective line width. So this finite and natural width of the atomic spectrum results from a number of phenomena. These are also given below: the uncertainty and Heisenberg broadening. This arises due to uncertainty in the energy of the excited state. Then collisional broadening. It is due to distortion of the outer energy levels arising as a consequence of the collision of other atoms. Then Doppler broadening. It is due to shift of the frequencies of the emitted photon due to relative motion with respect to the detector. Now coming to principle of flame photometry. The IUPAC, according to IUPAC, the name of the flame photometric technique is FAES, that is flame atomic emission spectroscopy. So the flame photometry done according to IUPAC, IUPAC recommended the abbreviation of FAES, that like flame atomic emission spectroscopy. So now let us discuss about the processes occurring when the solution of an analyte will put into the flame. So the first one is fate of the sample in the flame. In a typical flame photometric experiment, a solution containing relevant substance to be analyzed is aspirated into the burner. So that means the analyte substance will be aspirated into the burner of the flame and dispersed into the flame as fine spray. This phenomenon is called as nebulization. In the flame, the solvent evaporates fast. So when the analyte will be sprayed into the flame, first the solvent will evaporate, leaving finely divided solid particles which move to the hottest region of the flame, where the gaseous atoms and ions are produced, because the solid particles, the finely divided solid particles will interact with the hottest region of the flame, and so that they will be converted into gaseous atoms and ions. The atoms are excited by absorbing energy available from the flame. As the excited atoms return to the ground state of lower energy, radiation of wavelength characteristics of the element is emitted. So the intensity of the emitted radiation is then measured, which can be related to the concentration of the element present in the analyte, which forms the basis of quantitative analysis. And following processes occur in the flame. So when the analyte sample in the solution state aspirated to the flame of the burner, so they will be dispersed into the flame as finely spray, and after that these phenomena will occur. The first one is desolvation. The sample containing metal particles, that means the atomic particles, is dehydrated by the heat of the flame and the solvent is evaporated fast. When they will interact with the hottest zone of the flame, the solvent will evaporate fast, and after that vaporization, the heat of the flame vaporizes the sample constituent. No chemical change takes place at this stage, and then atomization at this stage. The metal ions where the solvent are reduced to metal atoms. For example, if metal ions will be there, suppose magnesium ions will be there in the solution state, they will first reduce to magnesium atoms in the gaseous state by heat of the flame and the action of the reducing gas. So here the gas present in gas is the reducing gas, and the molecule and ions of the sample species are decomposed into and reduced to give separated atoms. Then coming to the excitation state. The atoms of this stage are able to absorb energy from the heat of the flame, and the amount of energy absorbed dependent upon the electrostatic forces of attraction between the negatively charged electrons and positively charged nucleus. And after that, and this is and this depends upon the number of protons in the nucleus. As the electrons absorb energy, they move to the high energy levels, and then they will be in the excited state. Now coming to the last step, that is the emission of radiation. The electron in the excited state are very unstable, and they immediately come back to the ground state or lower energy state quickly. As they do so, they emit energy in the form of radiation, that is in the form of radiation of characteristic wavelength, which is measured by the detector. For some metal, this radiation corresponds to wavelength of the light in the visible region of the electromagnetic spectrum, and is observed as a characteristic color to the flame. That means for some particular metals, when the electrons will come back from the ground state to the lower energy state, or when the electron will come back from the excited state to the ground state or some lower energy state, so they will emit electromagnetic radiation with characteristics wavelength. And for some particular metals, these characteristics wavelength fall in the visible region. That's why you can observe characteristics color of the flame. As electrons from different energy levels are able to emit light as they so relax, that means when they will come back from the excited state to the ground or lower energy state, the electrons will be so relaxed, and the flame of the color observed will be a mixture of all the different wavelengths emitted by the different electrons in the metal atom under investigation. And this gives back the diagram, and the diagram is of the total process is mentioned here. You can see. So this is the diagram of the total process. First, so from the nebulizer, that the analyte solution will be sprayed to the flame, and where first the solvent will undergo desolvation. After that, solid gas or aerosol will form. They will undergo volatilization to form gaseous molecules. Then the molecules will undergo dissociation to form atomization, that is dissociation to form separated atoms. And after that, they will undergo ionization, because when they will interact with the hottest zone of the flame, this type of phenomenon will occur. After that, the atoms will undergo ionization to form atomic ions. And so here, during the process, the gaseous molecules may also undergo excitation, and the excited molecules again come back to the ground state by emission, that is called emission spectra. They will also, so there will be a chance of emission spectra, that is called molecular emission. And after dissociation, the atoms again undergo excitation by absorbing energy from the flame, and they will move to the excited state. After that, they will undergo emission, and they will emit electromagnetic radiation of particular wavelength. And similarly, the ions may undergo excitation. These are called excited ions, and after that they will come back to the ground state by emission of electromagnetic radiation of particular wavelength. And here, to filter the monochromator, all this emitted light will pass through the filter or monochromator, so that we, we can measure the required wavelength of light emitted by the species. And this is the diagrammatic representation of the process occurring in the flame obtained from any hydrogen flame. So the flame emission spectrum of the element of sodium can be obtained by placing a solution of sodium chloride in a suitable flame at the temperature of the flame should be around 2000 degrees Celsius to 3000 degrees Celsius. The outer of the electron of the sodium atom is promoted from the ground state 3s orbital and excited to p orbitals, that may be excited to 3p, 4p or 5p orbitals, and after that the relaxation of the excited electrons gives rise to characteristic emission spectrum of sodium atom. The emission spectrum of the sodium atom is relatively simple and consists about 40 signals or 40 lines. The most prominent emission signal being the region at 285 nanometer, 330 nanometer and 590 nanometer. That's, and the figure shows the portion of the flame emission spectrum of the sodium atom which is obtained by placing a sodium chloride solution with suitable flame. So here you can see, so these are the emission spectrum of the sodium atom obtained from the oxyhydrogen flame. So when the sodium chloride solution interact with the oxyhydrogen flame, so the sodium atoms will give rise to this type of emission spectrum. So that is called flame emission spectrum. And after that you will observe an intense signal at 589 nanometer in the emission of the sodium atom. This in fact consists a pair of lines around 589 nanometer and 589.6 nanometer, which could not be resolved due to instrumental limitations. The pair of the lines originate from the relaxation of excited electrons in the 3p to the 3s energy levels is responsible for the characteristic yellow glow of the sodium light. And the original signal can be rationalized in terms of energy level diagram. So this is the energy level diagram. From the energy level diagram you can see this is the energy level diagram of the sodium atoms present in the sodium chloride solution. So this is the ground state of the electron present in the sodium atoms in the sodium chloride solution. So when the sodium atoms will gain energy from the oxyhydrogen flame, they will undergo excitation. So during the excitation process, the electron may excite from 3s energy level to 4p, or may excite to 3s energy level to 4p, that may excite from 3s energy level to 5p, and that may also excite from 3s energy level. Sometimes that is 3p, that may excite from 3s to 4p or 3s to 5p or 3s to 6p. Now in the excited state, the electrons present in the 4s in the 4p, 5p and 6p energy levels will come back to the ground state or lower energy state. So if they will come back to the lower energy state, so they may directly come back to the ground state, or they may indirectly come back to lower energy state and after that ground state. So and for the atoms where the electrons will come back from higher energy to 3p energy level, and we know that, so these are the two degenerate 3p energy levels. From the 3p energy levels, again the electron come back to the ground state 3s energy level by emitting yellow colored light which is having wavelength 589.6 nanometer or 589 nanometer. So that's why you can observe yellow glow to the flame of the oxyhydrogen flame. So fraction of atoms in the excited state of different elements are at various temperature. Now if sodium atom will present, the emission line will appear at 589 nanometer. Similarly, for potassium atom, the emission line will appear at 767 nanometer. For lithium atom, that will obtained at 670 nanometer. For calcium atom, 422 nanometer. For magnesium atom, 285 nanometer. Now, from the wavelength of the emission line, we can characterize which element or which metals are present in the analyte solution. Now coming to flame and its characteristics. A flame can be so that means here we will discuss what are the different types of flames which will cause flame atomic spectroscopy. A flame can be described as a steady state gas phase reaction which takes place with emission of light. It is produced by burning a mixture of fuels and air or oxidant in a burner. The flame photometry, in flame photometry, a variety of fuels can be used, and the generally used fuels are air, oxygen, or nitrous oxide, that is N2O, and the flame temperature dependent upon the fuel to oxidant ratio. Now combination of a given fuel gas or air produces lower temperature as compared to when oxygen is used as oxidant. Alkali or alkaline earth metals are easily excited at low temperature obtained by using air. However, for heavy metals, oxygen or nitrous oxide employed as the oxidants. The the so requisite temperature of the analysis can be obtained by varying the fuel to oxidant ratio. So here in the table it is given. So these are the fuels: propene, acetylene, hydrogen. So these are the fuels, and these are the oxidant. The oxidants, the used oxidant, that may be air, that may be oxygen, maybe nitrous oxide, and the fuel oxidant mixtures and the attainable temperature. So when propene is used as a fuel and air will be the oxidant, then it can attain a temperature 22,500, 2250 degrees Celsius. And similarly, when propene will be used as a fuel and oxygen is the oxidant, then it can produce a temperature around 3070 degrees Celsius. The most commonly employed flames in the flame photometry can be grouped into two types: flames in which the fuel and oxidant as air or oxygen are well mixed before the combustion. These are called pre-mix or laminar flames, as they exhibit laminar flow. And the flames in which the fuel gas and the oxidant are fast mixed in the flame itself. They are called on-premix or turbulent flames, since they exhibit turbulence. Now we will discuss the structure of the flame. So flames are not uniform in composition, length or cross section. The structure of the premix flame, that is, here it is given the structure of the premix flame. So here this is the flame, and here the premix gases and the fine droplets of the solutions are introduced into the flame, and this is the primary zone of the flame, and here the interconal zone, and here the primary, below the primary zone, that is called preheating zone, and this is the secondary reaction zone. So the hottest zone is the interconal zone of the flame. So different zones of the flame are the preheating zones, primary reaction or inner zones, internal zones, and secondary reaction zones. The first or the innermost region of the flame is the preheating zone, where the combustion mixture is heated to a ignition temperature by thermal conduction from the primary reaction zone. And the second zone is the primary reaction zone, that is the inner zone. The zone is about 0.1 millimeter thick at atmospheric pressure and is visible by virtue of its blue green light observed to radicals of carbide radicals, CH radicals. There is no thermodynamic equilibrium in the zone, and the concentration of the ions and free radicals is very high. This region is not used for the flame photometry. And immediately above the primary reaction zone, that is the third or interconal zone, that is called reaction free zone, which can extend up to considerable height, and the maximum temperature is at chip just above tip of the inner zone. The highest temperature favors both production of free atoms. So that means after desolvation, the production of free atoms will take place in this zone, and the maximum excitation of the atomic emission spectroscopy will take place here. Therefore, this zone is used for the flame photometry. And the outermost, that is the fourth zone, that is called secondary reaction zone. Within this zone, the products of the combustion processes are burned to stable molecular species by the surrounding air. Now the reaction in the flames. So the first dissociation of the molecule will undergo dissociation into the isolated atom, and the rate of dissociation Kmx equals to Pm into Px by Pmx. And after that, formation of compound with the flame components. So the atoms, after dissociation of the molecules, the metal atoms will react with the flame component to form a compound, and after that ionization of atom will take place. The atoms will interact with the hottest zone, that will undergo ionization to form M plus from M. So P is the partial pressure of the species, indicating the subscript. The partial pressure of the flame gas component is much larger than the partial pressure of the given element. It is therefore considered the constant and introduced into the equilibrium constant. The most important flame gas component forming a compound with the elements are oxygen, hydroxyl, radicals, and hydrogen. The most common compounds formed in the flame burning with air or oxygen are the metal monoxides. For example, a major fraction of the alkaline earth metal is present as monoxide unless very fuel-rich flames are used. However, alkali metals practically do not form any type of oxide. Hydroxide species are present for some alkali and alkaline earth metals in the hydrocarbon flames. Sodium form practically no hydroxide, while the concentration of lithium hydroxide molecules often exceeds the atomic lithium concentration by a factor of 10. None of the alkali metal hydroxide emits spectral band in the visible or UV region, whereas the spectral bands in the alkaline earth metal monoxides can be used for the determination of these elements. Now the instrumentation for flame photometry. The flame photometry, the sample is introduced into the flame where it will undergo a number of processes leading to the formation of excited atomic species, and after that the excited atomic species will emit electromagnetic radiation. The radiation is then measured and suitably analyzed. The instrument used for the purpose is called flame photometer. It consists of the following component. The first one is flame atomizer. It converts the sample into excited atomic species, and that is contains the following parts. The first one is nebulizer and mixing chamber. It means it is a means of transporting homogeneous solution into the flame to a steady rate. So the function of the nebulizer and mixing chamber, from the nebulizer and mixing chamber, the homogeneous solution will be transported into the flame with a steady rate, and after that atomic burn up. Here the fuel and oxidant burn to give the flame, then that can be maintained in a constant form and constant temperature. And after that monochromator, it isolates the light of the wavelength to be measured from the emission by the excited atom. And after that detector, it helps in measuring the intensity of the radiation emitted by the flame. After that amplifier and readout device, it is used to amplify the signal and provides a suitable output. And here the schematic diagram showing the layout of various components of the flame photometer. So here this is the mixing chamber and nebulizer. From this mixing chamber and nebulizer, the analyte sample in the solution state will be passed into the flame. And here this is the flame, and here this is the hottest zone of the flame. And first here the desolvation will take place, and after that will convert it into atoms, and here the atoms will undergo excitation by absorbing energy from the hottest zone of the flame, and after that they will emit electromagnetic radiation. The radiation will pass through the lens and filter, and after that that will analyzed through the photodetector and amplifier, and will be amplified in the readout device. And here you can see this is the analyte solution that will introduced into the mixing chamber and nebulizer. Then the detailed process will carried out. So first we will discuss the different components of a flame pattern photometer. The first one is flame atomizer. The role of the atomizer to generate vapors of the analyte which get excited by the thermal energy of the flame and then emit characteristics radiation that is measured. The flame atomizer assembly consists of two components. The first component is the nebulizer, where the sample in the form of solution is drawn and converted into fine mist or aerosol. It is then passed into a second component, that is the burner, along with the air or oxygen as the fuel gas and the fuel gas. In the flame, the number of processes occur that convert the analyte sample into excited species. Let us learn about the nebulizer used in the flame photometers. So different types of nebulizers are present. Now nebulizer is a device that is used for the sample introduction into the flame. The process is called nebulization and consists of thermal vaporization and dissociation of aerosol particles in high temperature, producing small particle size with high resident time. A number of nebulization methods are available. So the first is pneumatic nebulization, ultrasonic nebulization, electrothermal nebulization, and hydride generation. So the fourth one, that is hydride generation, used for certain elements only. So first we will discuss the pneumatic nebulization. So that is the most commonly used nebulizer for introducing aqueous or liquid samples. In this, the sample solution is fed or aspirated into the nebulizer, which convert the liquid into the fine mist or aerosol, which is then fed into the flame. A common type of pneumatic nebulizer is called concentric pneumatic nebulizer, as shown in the figure. So here you can see, so this is the liquid input, so that is concentric type of pneumatic nebulizer. So here, this is the nozzle. So here the liquid solution will transported into this, and after that they will be converted into fine mist or aerosol, and here that is the gas input. So that will mix with the gas. So here gas input. So when the solution interact with the gas, that will convert it into fine mist or aerosol. After that they will be fed to the flame through the nozzle. Now coming to atomizer burners. The sample is introduced from the fine spray at a controlled rate into the flame to a burner with the help of nebulizer. In the burner, the analyte undergoes a number of processes as mentioned earlier. Two types of atomizer burners have been used in the flame photometry. So the first one is premix burner and the second one is total consumption burner. So in the premix burner, the solvent of the smaller droplets evaporate partly fast in the mixing chamber, then in the conduit of the burner, and finally to the flame. Only drops of certain size can reach the burner are completely burned. Thus, the efficiency of the premix burner is very low, that is only 5% of the samples reach the burner, and the efficiency of the burner has been improved by putting the impact of bed immediately after the nebulizer. So the impact of bead has the effect of breaking up the large droplets. They come out from the nebulizer, thereby increasing the number of small droplets and efficiency of the nebulizer. So this is the schematic diagram of the premix burner. So here this is the burner head, and this is the diagram of the premix burner, and here this is the nebulizer. So through the nebulizer, the sample will pass through the mixing chamber. The premix burner are called Bunsen, Micker or slot burners depending upon where they have one large hole, a number of small holes or a slot of the outlet port for the gas mixture respectively. In case of burner contain several parallel slots, that is called multi-slot burner, or three, that is for a particular example, that may be three slot burner. The smaller diameter of the holes in the maker burner, narrowness on the or the narrowness of the slot in the slot burner usually prevent the unwanted flash back of the flame into the burner housing. The advantages of the premix burner is that it is quite accurate and the analyte signal is significantly less noisy than that of the total consumption burner. That will discuss here. And after that, the total consumption burner. A total consumption burner combines function of the nebulizer and burner. In this type of burner, the suction created by compression of oxidant streaming part of the inner capillary introduced to the sample directly into the flame event if it is induced suspended particle or large solvent droplets. Hence, that is called total consumption burner. So this is the schematic diagram of a total consumption burner, and here the efficiency will be more. And after that, monochromator. So the role of the monochromator is to disperse the radiation coming from the flame and falling on it. The dispersed radiation from the exit slit of the monochromator goes to the detector. In case of low temperature flame is used, the spectral line from only a few elements are emitted. In such cases, for the most routine analysis, a filter can be used for a material which are transparent in a small selective wavelength region. The filter chosen is one which has a wavelength range in which the transparent to the emission from the element of interest. In such cases, a condenser lens system is employed to collect the emitted light and send the rays through the filter as an approximately collimated beam to reach the detector. Now coming to the detector, the function of the detector is to measure the intensity of radiation falling on it. Photoemissive cells or photomultiplier tubes are commonly employed for this purpose. Now coming to amplifier and readout device. The output of the detector is suitably amplified and displayed in the readout device like a meter or a digital display. The sensitivity of the amplifier can be changed so as to able to analyze the samples of varying concentration. Nowadays, the instrument have microprocessor control electrons that provides output compatible with the printers and computes, thereby minimizing the possibility of operation error in transferring the data. Now coming to application of flame photometry. So the first one is qualitative application. Flame photometric methods are widely used for the determination of alkali and alkaline earth metals in the sample and that are easily prepared in the aqueous solutions. Some of the elements can also be detected visually by the color of the flame. For example, sodium produces yellow flame. However, this method is not very reliable. The best method is to use flame photometer with a filter or monochromator to separate the radiation into the characteristic wavelength of the different metals and other radiations present in the sample. If the radiation of the characteristic wavelength is detected, it will indicate the presence of that particular metal in the sample. Now coming to quantitative application. The concentration of various alkali and alkaline earth metals is important for determining suitable soil for cultivation. And very generally, analysis leaves of the plant for K plus, potassium and calcium ion is carried out. This gives the idea of concentration of these ions or in the soils which can taken up by the plant. For agricultural purpose, an analysis of a proper mixture of surface soil and subsoil is carried out to determine the fertilizer requirement of the soil. In all these analyses, the soil or the ash is evaporated to dryness with concentrated hydrochloric acid and the residue is treated with the water or dilute hydrochloric acid to get these ions into the aqueous solution. And similarly, in clinical chemistry, it is very important to determine the concentration of sodium or potassium ion in the body fluid, since their ratio controls the actions of the muscle, including the heart. Since these ions form few insoluble compounds and exhibit essentially no acidic or basic properties, they cannot be determined so readily by conventional wet chemical techniques and are usually measured instrumental. And similarly, very often internal standard lithium is added to take care of matrix effect. For example, for calcium analysis, lanthanum or EDTA must be added to the solution to avoid interference due to presence of phosphate. Food and drinks are usually analyzed by ashing and leaching out of the ash with mineral acid to reach out these elements. Soft drinks, fruit, fruit juice, and alcoholic beverage can sometimes be analyzed using flame photometric technique. So now this is the methodology of quantitative analysis. So in the quantitative analysis, so the standard calibration plot is usually linear plot over a wide range, but a device is generally observed at but if the device will be generally observed at low and or high concentration end. So let us have a close look of a typically observed calibration plot as shown here. So from this calibration plot, you can see three different regions of the calibration plot are distinctly visible. So the region which is marked as A, that is A, that shows very low concentration. So range, in this very low concentration range, emission falls below expected value due to ionization of some atoms are converted into ions. For example, potassium ionization is given as K, so the potassium atom will be converted into potassium ion, and such ionization, however, so that is insignificant at higher concentration. And the region mark B, that is called the linear region, which can be used for quantitative measurement. So for quantitative measurement, you can use this linear region, that is up to B, up to this, that is the linear region. And the region C is depicted at high concentration region, and in this region the concentration range is very high, so that's why negative deviation is observed due to self absorption. Photons emitted by the excited atoms are partly absorbed by the ground state in the flame. Thus the calibration curve method helps to finding the concentration of unknown samples. However, for some samples, it is difficult to prepare standards which are sufficiently similar. This may occur when the samples contain high or variable concentration of matrix material, or when the sample contains solid whose effect observed is hard to duplicate. In such cases, we need to resort any of the following method, that is standard addition method or internal standard method. So here the schematic diagram of the calibration plot of emission versus concentration of determination of sodium by standard addition method. So here, so this is the calibration curve. And some other applications are also there. The flame emission spectroscopy is called simultaneous multi-element analysis. A number of methods have been suggested for carrying out simultaneous multi-analysis. By using suitable detection system and monochromator, the resolution of 2 nanometer can be achieved, and the simultaneous determination up to 10 elements have been carried out by this method. In addition to the determination of metals, flame photometry can also be applied for the qualitative and quantitative measurement of nonmetals analysis by utilizing infrared region of the spectrum using flame infrared emission technique. And interferences in quantitative determination. So in quantitative determination, the success of the quantitative determination depends on how the accurately intensity of the emitted radiation is represented and the concentration of the analyte. It has been found that number of factors besides the analyte affect the intensity of the emitted radiation. So the analyte signals measured upon include contribution from the constitution other than the analyte. The constitutions are called matrix constituents, and the contributions are known as interferences and are found to influence the outcome of the analyte procedure. This can be corrected by subtracting their contribution to the signal, and the contribution of the interference can be calculated from the magnitude of the interference and concentration of the interference. So the interference can be classified as follow. First one is spectral interference, ionized interference, and chemical interference. So the first type of the interference arises when two elements exhibit spectra and which will be partially overlap and both emit radiations at some particular wavelength. So if two elements will exhibit spectra and both will emit radiation at some particular wavelength, and the detector cannot distinguish between the source of the radiation and the recorders of the total signals, thus resulting incorrect result. Some interferences are more common at high flame temperature because numerous spectral lines are produced at high temperature. For example, iron line at 324.73 nanometer overlaps with copper line at 324.75 nanometer. So that means the spectral line for iron atom at 324.73 nanometer and similarly for copper at 324.75 nanometer. Such interference can be overcome either by taking the measurement of an alternative wavelength which can no overlap if available, or by removing the interferencing element of it by extraction. Alternatively, one may make calibration curve which is prepared from the solution having similar quantities for the interfering element. And the second type of spectral interference deals with spectral line of two or more elements which close but their spectra do not overlap. So this type of interference becomes a problem when a filter is used as the device to isolate the spectral lines. A filter may allow the spectral lines to separate by 5 to 10 nanometer to pass through, thus resulting an error in the analysis. Such interference can be reduced by increasing the resolution of the spectral system, isolation system. However, the interference cannot be eliminated entirely due to fine width of the spectral isolated system and the fine slit of the such system. Then third type of spectral interference occur due to presence of continuous background which arises due to high concentration of salt in the sample, especially for alkali and alkaline earth metals. Some of the organic solvent also produce continuous background, and this type of interference can be corrected using suitable scanning technique. Now coming to ionization interference. In some cases, high temperature flame may causes ionization of some of the metal atoms. So that means some of the metal atoms will undergo ionization, so they will show different type of spectra. For example, in case of sodium, it gives the sodium atom at high temperature flame that may ionize into sodium ion. So the sodium ion possesses an emission spectrum of its own with frequencies which can different from that of the sodium atom. So this reduces the radiant power of the atomic emission, and the interference can be eliminated by adding large quantity of potassium salt to the standards as well as sample solution. The addition of potassium salt suppresses the ionization of sodium atoms as the potassium atoms itself undergo ionization due to low ionization energy. Thus, the sodium atom emission is enhanced. So this type of interference is restricted to alkali metals only. Now coming to chemical interference. Apart from this type of interference, some chemical reaction may take place between cation and anion, that is called cation anion interference, and cation interference due to oxide formation also. Now the merit and limitations of flame photometry. So these are the advantages. So these are the merit and the limitations. And after that, we will discuss the next technique, that is atomic fluorescence spectroscopy. So here we will start the next technique after 2-3 minutes of break. Then we will start. So now we will discuss about the atomic fluorescence spectroscopy. Now coming to origin of atomic fluorescence. First one is atomic fluorescence spectrum. In an atom contains a set of quantized energy levels that can be coupled by the electrons depending upon the energy. The atoms obtained by the process of atomization in a low temperature flame are primarily in the ground state. So when exposed to an intense radiation source containing of radiation that can be absorbed by the atoms and get excited, and the source can be continuous source like xenon lamp or line source like hollow cathode lamp, electrode less discharge lamp, or tuned laser. And the radiationally excited atoms relax back to the ground state, accompanied by a radiation, and the phenomenon is called atomic fluorescence emission. The radiative excitation and de-excitation processes for the annulate AFS measurement are in UV visible range. The intensity of the emitted light is measured with the help of a detector which is placed in the direction perpendicular to that of the incident radiation and absorption cell. A plot of the measured radiation intensity as a function of the wavelength constitutes the atomic fluorescence spectrum and forms the basis of analytical fluorescence spectroscopy technique. Now, the types of atomic fluorescence transitions. The fluorescence emission can occur through different pathways as we have different types of atomic fluorescence transitions. The most common type of atomic fluorescence transitions are given below. The first one is resonance fluorescence, then Stokes direct line fluorescence, stepwise line fluorescence, two-step excitation or double resonance fluorescence, then thermal fluorescence, then sensitized fluorescence. So first we will discuss the resonance fluorescence. The resonance fluorescence occurs when the excited states emit a spectral line having same wavelength that is used for excitation. Again, the resonance fluorescence occurs when the excited states emit a spectral line having the same wavelength as that is used for excitation. And the figure gives a origin of the resonance fluorescence line in terms of the schematic energy levels. So here, this is the wavelength of excitation, and here the emission spectra will having same wavelength that of the excited lines. So that will give rise to resonance fluorescence. When magnesium atoms are exposed to UV light source, a radiation of 285.2 nanometer is observed and leading to excitation of the 3s electron into the 3p energy level. So here the 3s electron will undergo excitation into 3p. And after that, this then emit a resonance fluorescence radiation at the same wavelength, which can be used for the analysis. And the origin of the resonance fluorescence in case of magnesium atom is given in this diagram. So that means when the magnesium atom is used as the analyte, and when that will exposed to UV source of radiation of 285.2 nanometer, that will undergo the electrons present in the 3s energy level will undergo excitation into the 3p energy level, and in the excited state again the electron come back to the ground state 3s energy level by emitting radiation of same wavelength. So that is called resonance emission spectrum. The next one is Stokes direct line fluorescence. The Stokes direct line fluorescence is observed when an atom excited to higher energy state by absorption of radiation and goes to lower immediate energy level by emission of radiation. For this intermediate level, it returned to the ground state by radiation-less process, and here a schematic diagram is here. First, the atom will undergo excitation to higher energy level, and from the higher energy level, so that will emit radiation in form of light. So that is called direct line fluorescence. And after that, from this intermediate energy level, that will come back to the ground energy level by radiation less deactivation process. So that means when the atom will come back from this energy level to this energy level, that will emit radiation less deactivation, that will emit energy which is not in the form of radiation. Here this is the schematic diagram. So the direct line fluorescence will always occur at higher wavelength than that of the resonance line which excites it. It is also called Stokes fluorescence. The advantages of using the direct line fluorescence is that it eliminates the interaction due to scattered radiation which is encountered in the resonance fluorescence lines. Now coming to stepwise line fluorescence. In this type of fluorescence, an atom initially excited to higher energy state by absorption of radiation undergoes deactivation by radiation less process to some lower excited state, and from that lower excited state it emits radiation and return to the ground state. It is also a type of Stokes fluorescence, and here the schematic diagram is there. First the atom will undergo excitation, and from the excited state it will come back to some intermediate excited state by radiation less deactivation process, and from that intermediate excited state it will come back to the ground state by emitting fluorescence. That is called stepwise line fluorescence. And after that, two-step excitation or double resonance. The double resonance technique involve the double resonance fluorescence involves two-step excitation process using two dye lasers. The first laser excites the analyte from ground state to a particular excited state, from where it further gets excited into another higher excited state with the help of a second laser, and the de-excitation of this higher excited state to the lower energy state is accompanied by fluorescence emission. This is called double resonance fluorescence. You can see the first atom will undergo excitation by a particular laser. Then again from this excited energy level, it will go to further excited energy level by second excitation process using a second laser. And after that, from the second excited state, it will come back to the first excited state by emitting light, that is called double resonance fluorescence. So the fluorescence emissions occurs from both the excited energy levels. In this case, part of the emitted radiation has the shorter wavelength as compared to that of the excited radiation. It is also called anti-Stokes fluorescence. The origin of this type of fluorescence in terms of energy level diagram is shown here. Now coming to sensitized fluorescence. In sensitized fluorescence, the energy of the excited atom is the energy of the excited atom the energy of the excited atom is transferred to another atom which gets excited and relax back, accompanied by fluorescence emission, and the process of sensitized fluorescence emission can be represented below. So here this is the excited atom, and the energy of the excited atom is transferred into another atom A. So the initially excited atom will be de-excited by transferring energy to another atom A, and the another atom A will undergo excitation, and the second atom will emit fluorescence spectra. Now coming to principle of atomic fluorescence spectrometry. First one is fluorescence intensity and analyte concentration. There are two main purposes involving the fluorescence emissions which are given below. First one is absorption of radiation to generate excited atoms, and the second one is de-excitation of the excited atoms by emitted radiations. When the radiation intensity of P0 is passed through an analyte of concentration C moles per liter taken in a cell of thickness B centimeter, then the intensity of the transmitted radiation of the analyte is governed by Lambert's-Beer's law, that is P equals to P0 into e to the power minus epsilon Cb, and the amount of light absorbed, that is P ABS, equals to P0 minus P, that is equals to P0 whole into 1 minus e to the power minus epsilon Cb. Then the intensity of fluorescence Pf is proportional to quantity of radiation, that is Pf is directly proportional to PABS, which is equals to PABS into some constant phi. So Pf equals to P0 whole into 1 minus e to the power minus epsilon Cb into phi, where Pf is the intensity of the fluorescence, PABS is the quantity of radiant energy absorbed, phi is the fraction of the excited atom to ground that undergo fluorescence when epsilon Cb is very small. So Pf equals to P0 into 2.303 epsilon Cb into phi. Thus, the fluorescence intensity is directly proportional to its concentration. In quantitative AFS, the instrument is generally standard by calibration curve. The graph is drawn below in the logarithm of the intensity of the atomic fluorescence signal versus the logarithm of the analyte concentration. You can see the linear relationship between the concentration of the fluorescence intensity extends over 3 to 5 records, 5 orders of magnitude. However, it is valid only at low concentration of the element. At higher concentration, when fluorescence emissions is high, part of the emitted light will be absorbed by the atom in the ground state. This is called self-absorption. It will lower the intensity of the emitted radiation and proportionality will be lost. Further, the efficiency of the fluorescence emission is lower if the atoms in the excited state lose their energy by radiation-less process, that is by collision with other atoms, where the energy of the excited state is transferred to the vibrational energy levels of these atoms. And the mechanism of deactivation of the element of the excited state, that is called quenching. The proportion of the deactivation by quenching mechanism can be decreased by surrounding the atomization flames by noble gases like argon or by using non-flame methods to convert the sample into atoms. Now we will discuss the instrumentation for atomic fluorescence spectrometry. The atomic fluorescence spectrometer consists of the following essential components. The first one is the radiation source, atom reservoir, monochromator, detection system, readout device. The equipment is used similar to that is used in atomic absorption experiment, except that the detector is put in the position perpendicular to that of the incident radiation. The remaining part will be same. A block diagram showing the different component and their relative arrangement is shown below. So this is the radiation source, this is the flame reservoir, and here wavelength selector, photoelectric transducer, that is the detector, then the signal processing and readout device. So here this is the schematic representation of atomic fluorescence spectrometer. The first one is radiation source. The different types of radiation source are used for atomic fluorescence spectrometer. The first one is hollow cathode lamp, that is called HCl. Then electrode-less discharge lamp, EDL. So these are the components are here explained. Then atomic reservoir. The next one is cold vapor cell hydride generation. Now coming to monochromator, the fluorescence emission from the fluorescence emission from the excited atomic species is generally dispersed by a monochromator. The monochromator are the devices that select a given emission line and isolate it from the other lines due to molecular band emissions and all non-observed lines. The most commercial instrument use the diffraction gratings for this purpose. These gratings instruments can maintain a high resolution over a range of wavelength. In laser-induced ionization spectrometry, no spectral isolation is required at all. Now coming to detector, the emission radiation dispelled by the monochromator or the filter is sent to the detector. Here, the signal is detected by PMT, as in case of the flame photometric or atomic emission spectroscopy. After that, readout device, the output from the detector is suitably amplified and displayed in the readout device like a meter or digitally display. Now, application of atomic fluorescence spectrometry. So, the atomic fluorescence spectrometry has been used in the analysis of more than about 60 different elements present in diverse variety of samples. The general use of the AFS is to determine the concentration of elements in the sample. That is for elemental analysis. In favorable condition for some elements like cadmium, lead, the detection limits in the syringe is around 10 to the power minus 18 gram have been obtained. The quantitative analysis using AFS can be carried out by employing the standard calibration plot method and standard addition method in case of other spectrometric methods. Then the clinical use, that is analysis of lead, mercury, arsenic, antimony, bismuth, germanium, selenium in blood, urine, tissue, nail, hair, and copper, zinc, and lead in blood serum and urine samples. For environmental analysis, it will be used for the determination of mercury at 1 nanogram levels, arsenic, selenium, antimony, tellurium with the detection limit between 10 to 50 nanogram levels in environmental samples. Mercury in the air can be determined at levels as low as 10 picogram. Determination of femtogram, that is 10 to the power minus 15 gram quantities of element in the sample by graphite furnace or laser excitation AMS, AFS can also be done. And agricultural application, that is analysis of dairy, wine, feed, meat, cigarettes and other products for the elemental analysis of arsenic, mercury, lead, antimony, selenium. Then geological and metallurgical application for analysis of ore, rock, mineral, metals for germanium, mercury, selenium, arsenic in antimony, selenium, tellurium in copper, and similarly pharmaceutical application for determination of mercury, lead, arsenic, selenium in active ingredients and fillers. And for petrochemical, it is used for the quantitative determination of mercury, lead, cadmium, arsenic, tin, zinc in fuels, lubricant, and crude oils. And for alloy, some of the example of the element determine the alloy are copper, iron, magnesium, manganese, nickel, zinc. With combined with chromatography, AFS can provide qualitative and quantitative information on chemical from the element, that is called metal speciation in the sample. So these are the some common elements using in the atomic fluorescence analysis and their corresponding emission wavelength, and here these are the detection limits in nanogram per ml. Now coming to interference, the interference are produced by sample matrix, that is the non-annuled component of the sample. The interference could be chemically arising out of the molecular species containing the annulate, which in turn reduce the percentage of the gaseous annulate or spectral due to radiation of other atomic fluorescence. So these are the spectral interference, chemical interference, and after that merits and demerits of this technique. And then we will discuss the next analytical technique, that is called atomic absorption spectrometry. Now coming to the principle of atomic absorption spectrometry AAS. Now according to Boltzmann distribution law, the population of the ground state, that is the number of species in the ground state, is highest and it keeps on decreasing as you go to the higher energy level. It can be shown that for most of the elements at moderate temperature in the flame, nearly all the atoms are in the ground state, leaving out few atoms in the excited state. Now, according to so the absorption follow the Lambert-Beer's law, so that the concentration of the analyte element in the vapors in the flame may be determined. Now, according to Lambert-Beer's law, the extent of the radiation absorbed by the observing species is a function of path length and the concentration of the observing species. Mathematically, log P0 by P equals to epsilon BC, where P0 is the intensity of the incident radiation, P is the intensity of the transmitted radiation, B is the thickness of the observing medium, epsilon is the absorption coefficient, and C is the concentration of the observing analyte atoms. And log P0 by P is called the absorbance, that is represented by A. Therefore, A equals to epsilon BC. Thus, the absorbance of the sample is directly proportional to concentration of the analyte because epsilon B are constant. Therefore, a calibration plot of the concentration of the analyte element versus the absorbance is drawn from the standard solutions, and after that the concentration of the element in the unknown solution can be determined from the graph. However, such a linear relationship between the absorbance and the concentration can be observed if all the radiation passing through the sample is absorbed and some extent by the analyte atoms. However, experimental concentration versus intensity of the calibration curve is observed to be deviating from the linearity as the result due to the presence of non-absorbed radiations and other interferences. So in the quantitative methodology, like many other analytical methods, AAS is also not an absolute method for the analysis. The routine analytical methodology for quantitative determination using AAS is based upon the calibration method. Besides this, the internal standard method and standard addition methods are also employed. The first one is calibration method. So the calibration method is divided into two types, that is three standard calibration method and one standard calibration method. So in this method, a calibration plot is drawn by aspirating standard solution of known concentration into the flame and measure the observance of each solution. The concentration of the unknown solution is then determined from the calibration plot. Despite the fact that Beer's law is followed in the AS, in practice, deviation from the linearity will be observed. The non-linearity will be due to transmission of the unobserved light from the radiation source. In addition, a number of uncontrolled variables in the atomization and observation measurement may also affect the measurement. In practice, a single calibration curve does not serve this purpose. We need to take 3 to 4 standard different concentrations and a bank to obtain suitable calibration plot. A standard calibration plot does not hold good. Further, if the analyte concentration happen to be outside the limit of the standard used by the calibration, then the analyte should be suitably diluted or concentrated. So first one is internal standard method. In the internal standard method, a fixed amount of internal standard which is chemically similar to that of the analyte being determined and the observed at similar wavelength is added to the standard solution and to the test sample. The intensity ratio of the analyte and internal standard is plotted as a function of analyte concentration in the standard solution. For example, people determine for the determination of sodium or potassium in blood serum, lithium is used as internal standard. A typically plot obtained from the atomic absorption spectrometer is shown here. So this is observance of the analyte versus observance of the standard, and the x-axis is the concentration of the analyte. Now standard addition method. This method is especially applicable when the signal is altered by sample matrix. In this method, known amount of the standard solution of knowing of known increasing concentrations of the analyte is added to a number of aliquots of same solution. The resulting solution is diluted to some final volumes and their observance are measured. A graph is drawn between the observance and the added concentration of the analyte. It is then extrapolated to the concentration axis to obtain the concentration of the sample solution. If a plot is non-linear, then the extrapolation is not possible. It is essential to perform blank correction in such cases. Now coming to the instrumentation for atomic absorption spectrometry. So the instrumentation, a typical atomic absorption spectrometer consists of the following components: radiation source, atom reservoir, monochromator, detector, and so readout device. So these are the schematic diagram of the atomic absorption spectrometer showing the basic components. In a typical flame atomic absorption spectrometric determination, the radiation from a hollow cathode lamp is made to fall on the sample of the analyte aspirated into the flame, where part of it is absorbed and the transmitted radiation is then dispersed by the monochromator and sent to the detector. The detector output is suitably processed and is displayed by appropriate readout device. This signal channel, the instrument can perform measurement at single wavelength only on one channel. Nowadays, the dual chamber instruments are also available for permit simultaneous measurement of two different wavelengths. These contain two independent monochromator for this purpose. Thus, this can be used for the simultaneous determination of two elements. And here this is the radiation source. Similar type of radiation source are nowadays hollow cathode lamp belonging to the first type and the most widely used, and the next one is electrode less discharge lamp EDL. Then atomizer. The purpose of the atomizer to provide a representative portion of the analyte into the optical path and convert into free neutral ground state atoms, and the atomic absorption spectrometry. The names, the flames and the furnaces are the flames and furnace that generate temperature in the range around 1500 to 3000 degrees Celsius. Then flame atomizer. Then burners, similar type of burners, pre-mix nebulizer burner and total consumption burner. Two types of burners are there. And after that monochromator, then detector. And finally the readout device. Then different atomic absorption spectrometric techniques are there. The first one is graphite furnace atomic absorption spectrometry. So these are the graphite. So in order to overcome the problems arise in the flameless method, AAS have been developed. Two types of flameless atomizers are generally used. These are graphitic tube, and the carbon rod or filament. AAS using the graphitic furnace is called graphitic furnace atomic absorption spectrometer, GFAS. And now the next one is electrothermal atomizer. So here that is the graphite furnace is there. Instead of using flame, graphite furnace are used. Then atomic absorption spectrophotometer. So two types of atomic absorption spectrophotometers are given below. The first one is single beam atomic absorption spectrophotometer, and then double beam atomic absorption spectrophotometer. And then similar type of interferences in atomic absorption spectrometer: spectral interferences, chemical interferences, physical interferences, and the sample handling in atomic absorption spectrometry, preparation of sample. So these are the methods. That is use of organic solvent for preparation of sample, then microwave digestion, then sample introduction method, similar pneumatic nebulizer, ultrasonic nebulizer, electrothermal vaporization, and hydride generation. So these are the different techniques in which the samples are introduced into high energy state, then application of atomic absorption spectrometry. So that is widely employed techniques for trace and ultra trace analysis of complex matrices in geological samples, biological samples, environmental, industrial, glass samples, cement, marine sediment, pharmaceutical samples, engine oil, or any kind of samples. It has been employed for the determination of more than 60 elements at a trace and ultra trace level. It is frequently used for the cases where the sample size is small and in case of metal proteins also. So the resonance lines are and the approximate detection limits of some detected elements by flame AS and GFAS. Both the techniques are same, only here flame is used as the source of excitation, but in case of GFAS, graphite furnace is used as the source of excitation. And these are the merits and demerits. So today we'll stop here. The remaining techniques will conclude tomorrow. Okay? Hello? Hello?
हाँ, okay, sir.
Okay.
Okay, thank you, sir.